Hello, this is Seamus. I am PCC and postdoctoral fellow at Princeton University. In my talk, I will discuss multifunctional boron nitride polymer composite aerogels. First, I will give some quick information about aerogel composites and 2D layered material-based aerogels. Then I will discuss HPM polymer composite aerogels, and I will finish my presentation with conclusion and acknowledgement. Aerogels are porous solids with properties of low density, high porosity, high surface area, and high resistancy. These properties makes these materials potentially to be used in a broad range of applications, including aerospace applications, automotive industry, building insulation, environmental applications, packaging, and energy applications. Currently, aerogel technologies face many challenges. Most important challenges are manufacturing processes, cost-effective production, and material durability. Underlying the manufacturing challenges is the critical need for greater control assembly of the molecular building blocks of aerogels. Controlling the manufacturing process offers a great opportunity to overcome challenges of tuning the density, mechanical, and thermal properties of aerogels. Cost-effective production is necessary for commercialization and integration of these structures into current technologies. Material durability is another challenge of aerogels. For example, most of these structures are brittle and they lose their properties at high temperature. That's why the design and synthesis of new aerogels with exceptional long-term stability and keeping their outstanding properties at different environmental conditions, including high temperature and high pressure, is needed for the integration of these structures into current technologies and for their commercialization. During last decade, 2D layered materials received an attention for creating new excellent aerogels because these 2D structures have higher dimensionality compared to zero-dimensional and one-dimensional nanostructures. And this gives 2D layered materials a great advantage for developing ultra-lightweight, mechanically robust, and fire-resistant hierarchical aerogels. Among these 2D nanostructures, HPN has attracted significant interest because of its electrical insulation and outstanding thermal and chemical stability. To date, although various HPN-based aerogels and their polymer composites have been fabricated, developing mechanically robust HPN-based aerogels with control over properties still remains a big challenge. Toward this aim, here we use solid ammonia borane as a precursor and polystyrene nanoparticles as a template. And mixing ammonia borane and polystyrene nanoparticles leads to the formation of self-assembled hybrid nanocomposite of ammonia borane and polystyrene. Key here is that ammonia borane absorbs on the surface of polystyrene nanoparticles because of intermolecular interactions between ammonia borane and polystyrene nanoparticles. At high temperature annealing of this hybrid nanocomposite of ammonia borane and polystyrene results the formation of an aerogel. Here the mechanism is the molecular ammonia borane absorbs on the surface of polystyrene nanoparticles and decomposes into the amino borane at 100 degree, around 100 degree. And around 150 degree, the structure turns to borazine molecules. And borazine is the main building block for HPN synthesis. Here, borazine undergoes dehydrogenation and produces interconnected HBN nanosheets on the surface of polystyrene nanoparticles when we increase the temperature to 1100 degree under nitrogen atmosphere. After we remove polystyrene nanoparticles by decomposition at 600 degree under air, the ultra lightweight HPN aerogel with interconnected spherical porous structures forms. The resulting HPN aerogel is ultra lightweight with a density of 6.4 milligram per centimeter cubic. Here we use Raman spectroscopy to determine the bonding characteristic and phase purity of the HPN aerogel. And Raman spectroscopy shows the characteristic E2G phonon mode of the HPN. In addition to Raman spectroscopy, we used XPS analysis to quantify the chemical analyzing of the HPN aerogel. Here in the XPS characterization, in addition of the boron and nitrogen atoms, we observed carbon residues and oxygen atoms. This is most probably is coming from carbon and oxygen residues are coming from the polystyrene nanoparticles residues after burning out the polystyrene. In addition to the spectroscopic characterization, we used SEM and TEM microscopic characterization to understand the morphology of HPN aerogels. Here, this SEM image shows that the HPN polystyrene composite before burning out the polystyrene nanoparticles. And the structures, as you see in the SEM image, is assemblies of the bubble-like structures. The structure of HPN aerogel after burning out the polystyrene nanoparticles is highly porous and interconnected cellular architecture with nearly spherical pore structures. Low magnification TEM image shows us a large folded HPN sheet with small HPN particles on the surface. And high resolution TEM image and diffraction pattern shows that the HPN structure is polycrystalline. And here in dark region, which are marked with arrows, shows multi-layer HPN sheets. Here we prepared the composite of HPN aerogel by infiltration of polymer additives into the HPN aerogel. Here we diluted PDMS, PMMA, polylactic acid, and polyethylene in toluene and immersed HPN aerogel into 5% polymer solution for overnight. The density of HPN polymer aerogels is much lower than bulk densities of the polymer and HPN as you see here. In addition, the density of the composite aerogel can be tuned by the tuning the concentration of the polymer solution. Here we showed as an example HPN PDMS aerogel. As you see here, the density of the HPN PDMS aerogel is increasing with increasing the concentration of PDMS solution. As a result of infiltration of 5% PDMS solution into the HPN aerogel, we obtained a flexible and foldable HPN PDMS composite aerogel. As you see in the image, the aerogel structure, the HPN PDMS aerogel, can repeatedly be bent and folded without destroying its structural integrity. Here SEM images also indicate that the HPN PDMS composite aerogel is still porous because the dilute pollution penetrates into pore structure and it doesn't feel whole pore structures. We performed the mechanical testing of HPN polymer aerogels, and here I will discuss the mechanical properties of HPN PDMS aerogels in detail. As you see here, the modulus of HPN aerogel decreased to 0.27 kilopascal and 0.65 kilopascal after penetration of PDMS and PMMA into the HPN aerogel. To further investigate the mechanical properties of HPN PDMS aerogel, we measured strain-dependent compressive test of HPN PDMS composite aerogel. As you see here, the compression stress-strain curve of the HPN PDMS composite aerogel shows the characteristic behavior of the porous sponge-like materials with 3 distinct stages. When the HPN PDMS composite aerogel is compressed until 40% strain, the composite aerogel deforms linearly with respect to the stress, which is the elastic region. The region between 40% and 70% strain exhibit elastic buckling and densification of the structure. With the strain above 70%, the HPN PDMS composite aerogel structure is compacted and behave like a bulk structure because of the reduced porosity. As you see here, when the force is released, the unloading curve returns to its origin without any measurable plastic deformation. The maximum stress for HPN PDMS aerogel is 82.4 kilopascal at 99% strain, and this indicates that this structure can tolerate a large deformation. And HPN PDMS composite aerogel shows exceptional hysteresis loop during compressive loading and unloading cycles, and this indicates that HPN polymer composite aerogel have a significant mechanical damping properties. To quantify damping capability of the composite aerogel, here we calculated the estimated dissipated energy. This dissipated energy corresponds to the area of the hysteresis loop during compressive loading and unloading cycles. Here we measured the dissipation energy of HPN PDMS composite aerogel at different strain. The energy dissipation here you see increasing with the increased strain. The energy dissipation mechanism here is expected to be beyond 2D structure of HPN because of the additional physical pi-pi, hydrophobic, and van der Waals interaction between HPN nanosheets and HPN polymer chains. As a result, the dissipation energy here indicate that mechanical damping properties of HPN PDMS composite aerogel can be explained by interfacial sliding between HPN nanosheets and HPN polymer chains. In addition of this, we showed the mechanical behavior, mechanical damping behavior of the HPN PDMS aerogel by using a 5 mm diameter steel ball, and the steel ball was dropped from a specific height onto the steel base and HPN PDMS composite aerogel, and from here we measured the height after rebounding. And then we calculated the resilience of the steel block 22% for 22.4%, and the resilience of the HPN PDMS composite aerogel is 31.6%. In addition, we measured the steady state thermal conductivity of aerogel by a homemade setup using thermoelectrical generator and infrared camera. Here we showed several examples to display the tunability of the thermal conductivity of these aerogels. Here we showed the thermal conductivities of the HPN PDMS, HPN polylactic acid, HPN polyethylene. In addition, we used iron oxide. We infiltrate iron oxide into the HPN aerogels and measure the thermal conductivity. HPN aerogel here is insulator because of its highly porous structure. And here, the highly porous architecture of the HPN aerogel efficiently reduces the air conduction and convection, and hence led to the thermal conductivities below that of the stationary air. Here, pore geometry, pore size, interconnection of the pores, and the thicknesses of the HPN walls affect the low thermal conductivity of the HPN aerogel. And we see clearly the thermal conductivity of the HPN composite aerogel increases because of the pore structure of HPN aerogel are filled with polymer additives. Here again, the thermal conductivity of HPN polymer aerogels are mainly determined by the heat capacitance of the polymer additives and interfacial thermal resistance of the polymers. In conclusion, here we report a promising approach to fabricate HPN composite aerogel with multifunctional of ultra lightweight, great resilience, and high energy dissipation that is associated with their mechanical damping behavior and tunable thermal conductivities. As I mentioned in the introduction, these materials can be used in a broad range of applications, including automotive industry, aerospace application, sound insulation, thermal platforms, packaging, and much more specific application area. I would like to thank the PCCM Postdoctoral Fellowship and Princeton University Innovation Fund, and I would like to thank to Rod and Craig for giving me an opportunity to work with them. In addition, I thank to Katie and Nikita for their contribution. Besides that, I want to thank to PCCM, PRISM, Chemical Engineering, and Mechanical and Aerospace Engineering of departments at Princeton University. Thank you for your attention. If you have any question, you can reach me out through my email here.